So I previously gave you an example of symplectic propagator, so let's do a symplectic propagator of the harmonic oscillator. So with that we need a little bit of math as well. So symplectic propagator of harmonic oscillator of Schrödinger equation. So we can define the Schrödinger equation, the lagrangian for the Schrödinger equation as such that it will be I. So we can, okay, I'm gonna have to do a little bit of math here. So I'm gonna define a Lagrangian density. Which will depend on psi and psi star, and it will look like this, that you have then and I think we need to, let's take the dot to here, and then we have the kinetic energy, and then we have the potential energy, potential operator, and both of these will be treated as a potential, and the kinetic term of the field will be given by this one. And now we basically the Euler-Lagrange equation for this now yields. So just to be complete, the Lagrangian will be defined in terms of the Lagrangian density. So, like so. So we integrate over the field. Yes. And the Lagrangian will be depending on the functions psi and psi star, and on dot psi and dot psi star. And of course the Lagrangian density will also depend on those. And now we can choose the Euler-Lagrange equation yields just the Schrödinger equation. So so we have something like partial of L with respect to the dot psi star with R, like so. Then time derivative of this one, and then we have just partial derivative with respect to psi itself, psi star itself, like so. So this is the Euler-Lagrange equation. I'm beforehand doing it with the complex conjugated one to get the real non-complex conjugated equation. So so this one will just yield the Hamiltonian, which is this one, and then this one will yield I psi and time derivative of that. So will just result into the Schrödinger equation. So so that will be I dot psi equals then the Hamiltonian multiplied by the wave function, like so. Now let's we can always add a total derivative to the Lagrangian density. So let's supplement the Lagrangian density with total derivative of I psi. So we add such function, and so 1/2 times I minus, okay. So we define a new Lagrangian density, which is the old Lagrangian density minus this one. So and now we can sort of get the new one. So it will cancel exactly half of this term, but then it will add a half of term where the dot has exchanged places. And this is just to change the variables. So we know this, so let me justify a little bit why we do this. So we notice that the generalized momentum which corresponds to the psi. So let's say so we take the pi star, and this will be the how you define a generalized momentum. It will be partial derivative of the Lagrangian density with respect to the dotted field, so time derivative field. And then if you look, it's here, so it will be I psi. So sort of these are almost so these things are like almost conjugate variables of each other, the psi and psi star. So that's not like the most optimal way, like because the psi is complex. So there's like so this one is complex and this one is complex, but they're dependent because they have the same real part and conjugated imaginary parts and so on. So this is not the most optimal way. So we look for some other coordinates, which would have only real quantities, so we get rid of the relatively complex. We don't want to be working in the complex plane. So we do this and get this one. And then we are sort of wise beforehand that we I know what the good coordinates are, so they are, so we substitute that the field psi will be in fact written as some real part and some imaginary part, like so. And the same way for the complex conjugated field, so like so. So we sort of do some sort of then minus here for the complex conjugate, so it's like we change into these two fields, and then there's psi star. Okay. And then we just have to be substitute this stuff, and we need to be a little bit careful. But essentially, if you look at these two, they're like the general structure of this stuff. There's like I divided by 2 here, and then this one is dotted and complex conjugated, and then this one will be complex conjugated, and this one will be dotted. So now we just have to, we can just blindly expand all of this. So it will be I divided by 2, then it will be dot r. I will just omit all the other stuff as well. Dot r times r, and then plus e dot I. So okay, let's do it like this, that first one, this one runs the fastest and this second fastest, so it will be still dot r and then I times I, and then it will be minus I dot I times r, and then it will be minus I dot I times I. So these two i's will be minus 1, so this one changes to plus. And then we're a few more terms to go. So this one, then minus r dot. Well, the minus r dot just cancels this one, like so. Then we have minus r imaginary part times I dot, and then that's, then we have minus, sorry, we have r times I dot, so it's this one, and that will be so, and then Did I wonder that yeah. So I will just write that explicitly out now. So we will have minus r I dot I, and then we will have two more terms. Oh, it's exactly here. Okay. So this one will be 2 times that one, and then we will have now we have then we have minus I dot r. So this one times this one, and then we have minus and minus, so it's plus. So this one also will have a factor of 2, and then we have the last term that will be minus I times I and dot I, and that will cancel exactly this one. So okay, so I believe then I can, this 2 will cancel here and here, and then this I we can cancel that as well, so we have minus and plus. Okay, so we actually can now have the new Lagrangian density, and it will be minus r minus dot r times I, and then plus r dot I. Okay, and then also we will have then the field r. So this one is Hermitian and real also, so the imaginary parts don't get mixed here, so there's complex conjugate of that one, so the cross terms will cancel each other. So we essentially have that we have like r, we have Hamiltonian appearing here, and also here. And now this will be a function of r and I and dot r and dot I. Okay. Now we have 2 variables and their time derivatives, and now we can do transform into Hamiltonian. So essentially this will be the Hamiltonian. So whatever will be the conjugate momentum of I, so we take partial derivative of L with respect to dot r, and that will be just minus I, and then we will multiply that with dot r. So so we're having so So where is my... So... end document was left here. Okay. So we have Hamiltonian, which will be defined. So conjugate momentum times the velocity itself, and then minus. And now we see that the Hamiltonian is actually linear. So with respect to these terms, so we take Lagrangian partial derivative of the Lagrangian with r prime. It will be just minus I, and then will be again times that. So it will, then we have subtraction of the Lagrangian density. So these two will be simply cancelled. And by no surprise at all, we actually get that the Hamiltonian actually, I mean, we already knew this, of course. We get the Hamiltonian looks like this. So we have R, and we have I, and then we have the Hamiltonian, and the Hamiltonian will have this just the kinetic energy operator and potential energy operator in its diagonal, like so. Okay, so what's up with this? And so the good thing is that if you recall the last classical mechanics video, this is actually exactly how a harmonic oscillator was defined as well. So we now know that the R and I are conjugate variables of each other, and we have like a way to generate symplectic propagators. So we can just do a split propagator. So we can propagate first by operating the real parts and then the imaginary parts, and that propagator will be symplectic. So let's see. Can we formulate an efficient and stable propagator using this method here? So I will call them. So here I have the VF function, and then I will say Q equals real VF and P equals image VF. So we have like momentum and position fields, and then we will say that Q equals Q plus Hamiltonian times P times dt, and then P equals to P minus Hamiltonian times Q dt. And then let's forget about the density matrix, but then let's just plot, for example, the real part of wave function, and then let's plot also our classical variable Q. And now these should equal. So, and we see that we have an unstable propagator. Let's see if we lower the time step. And we can see that the real part of the wave function operated using full matrix seems to be pretty much the same as the one I just implemented. So now we have a symplectic propagator for the Schrödinger equation.